defines a line in space? What elements define a line in space? Any point on the line, and? And what about that? How does that vector relate to the line? What is it about the line? How does that vector relate to the line? Yeah.
Same direction.
Same direction. Same rate. Well, no. So we don't have like an independent variable. This line is just kind of a static thing of points. So we haven't really started talking about rate of change yet. We will talk about rate of change. But you know that vector can have different magnitudes, right? And you still get the same line. So it's parallel to the line, or it could lie in the line, or points in the direction of the line, right? So that's what we mean by that vector. It's called the direction vector of the line. You could move it and set it right in the line, or you could say it's pointing in how the points the vector points in the direction of how the points would be swept out. That make sense? Okay, so planes. What about planes? So we're recording, right? What about planes? So now we want to define a plane. So like before, we're going to start with a point, but then we also need a vector that kind of gives like the direction of the plane. Well, what is that? The direction of first of all, what is a plane? Plane is different than a line in that it's a set of points. That's how it's the same as a line. A line is a set of points, but a line is like a straight string of points, right? What is a plane? A plane is a surface of points. So you could think of a line as kind of like a one-dimensional object, whereas a plane is two. It defines points kind of in two dimensions, right? So it's like the plane itself. You could write every point on a plane kind of if you had two coordinates, right? So it's a different animal, right? So a plane is, we do lines and then we do planes, but you got to, in your mind, it's a different type of set of points. Line is kind of a string of points, whereas a plane is a region of points, right? Two-dimensional. Okay, but we still are going to define it by a point in the plane and then some sort of direction, some sort of orientation of the plane. Okay? So what about like we said, the direction vector of the line, you could say it's parallel to the line or it lies in the line. What about a vector that's likewise is parallel to the plane or lies in the plane? Does that vector give us kind of the orientation of the plane? Does it like lock down how this thing is inclined in space? Does it lock it down? Some are saying yes, some are saying no. So if I just gave you that blue vector without the plane, okay, would you be able to say, yes, this plane is oriented like this in space? Again, some are saying yes, some are saying no. All right, the no's. Tell me what. So let me turn it off here. I'll turn off the plane. So if I just gave you that vector, would that imply that golden plane I showed you?
No, because you could like rotate it around the vector.
Right. You see, there's an infinite number of inclinations of planes that all contain that vector, like spinning a plane on an axis. Right. I need to make that animation. I'll have that animation next bit. So you imagine, given that vector, yeah, you could put a plane in there, but then you could give it a whirl, right? And then you'd have all these different inclinations. So a parallel vector doesn't do it. A parallel vector does not give us what we need in terms of locking down the orientation in space. Other ideas? What kind of vector could lock down that the plane is inclined like this and it's not going to move? John?
Something's perpendicular.
So what about an orthogonal vector? Would that lock down the inclination or how it's oriented in space? What do we think? Is there many orientations orthogonal to that vector, or is there only one in space? One kind of... Does that lock it down? Yeah, it does, right? So there's many planes that are orthogonal to that vector, but can you see that all those planes have the same like inclination in space, or same orientation? I don't really have a good word for this, but yeah. So what we're going to have is we're going to have a point, and we're going to have this orthogonal vector. And so another word for orthogonal when we talk about an R3, so orthogonal. So kind of the synonym is normal. So when we say normal, what we mean is orthogonal, and then when we're talking spatially in R2 or R3, that's perpendicular. So normal, orthogonal are pretty much the same. So we can use those terms interchangeably. Okay, so we call this vector for the plane the normal vector. The normal vector of the plane is the one that locks down its orientation in space. Okay, so we're going to put that normal vector, we'll put it at our point. So I've got my point here. So here's say this is the point I have. So I'm going to take this, mobiles or vectors are mobile, so I can move that normal vector anywhere I want. So I'm going to take that normal vector for my plane, and I'm going to put its tail right on the point that I have. Okay, so this point is a given point, so it's x naught, y naught, z naught. So as a vector, right? As a vector. Standard position vector, right? So standard position vector, its tip, the point at its tip is the same coordinates as the components of the vector, right? So that's that point, x naught, y naught, z naught. That's our given point. And then our normal vector to the plane is we're also going to often use ABC. So now you've got to keep your wits about you, right? Because what was ABC for a line? How did that vector relate to the line? What's that? Yeah, was it normal to the line? Parallel, right? So that direction vector of a line is the ABC is parallel to the line. The quote direction vector of a plane, the ABC, is normal to the plane. So you're going to be doing problems where you have planes and lines together. So you got to keep that straight, right? So what defines a line? Direction, it's parallel vector. What defines the orientation, inclination of a plane? It's normal vector. Conventionally, ABC is used for both. ABC is used for both of those. Okay, so we've got our point, we've got our direction vector. So, and then what are we going to have? We're going to have kind of like every point in the plane. So that's like this. Let's start going here. So you think of this now, this is now defining this vector defines every point in the plane. So what do we call that? So what are the components of that if it's every point in the plane? Just x, y, z, right? Right? It's just generically x, y, z. So the question is, how do we get every point in the plane, x, y, z, given x naught, y naught, z naught, and a, b, c? So it starts by taking this vector here. Look at this vector. You put the tip at the point. So it's a vector that's parallel to the plane. So its tail is at the point in question, and its tip is pointing at every point or any point in the plane. Like that. Okay, so can you write what that vector is? You should be able to. The vector whose tip is at whose tail is at the tip of x naught, y naught, z naught, our starting point in the plane. and whose tip is pointing at this generic every point in the plane. So what is that vector? Alyssa thinks she knows.
Subtract them, so it would be x minus x naught, and then y minus y naught, and z minus z naught.
Okay, what do you think? Is she right? Yeah, I started writing it, right? So she's right. Do you see that? So what is this? This vector is parallel to the plane, or you could set it in the plane, right? And so then if x naught is fixed, well, we let, you know, we let our x, y, and z vary. And so this vector, this x minus x naught, y minus y naught, z minus z naught, is always in or parallel to the plane. So we're pretty close to being able to write the equation. So now what do we have? What's always true then? If we look at the relationships of these vectors here. So what's the relationship of this parallel or kind of vector in the plane? This vector in the plane that starts at our known points and points at every other point in the plane. We have a relationship we can write. Yeah?
Something to do with like dot product? Or
So what dot product? Yeah.
well, you could say that the A, B, C, and then that vector is always going to equal 0 dot product.
So that vector that's starting at our known point and pointing at every point in the plane is how related to our normal vector. It's going to be normal, right? You see that? So this vector, since it's parallel to the plane and this is normal to the plane, those will be orthogonal. Therefore, dot product is 0. And that's what will define the equation of the plane. So here we go. So dot product is 0. So we're going to take A, B, C. Our normal vector to the plane, right? Our normal vector to the plane, dot. This parallel vector, which is x minus x naught, y minus y naught, z minus z naught. And we take the dot product, we get? Okay, so that will define our equation of the plane. What's variable and what's known or fixed? A, B, and C. Variable or known?
No.
It's known, right? So that's our orthogonal vector. How about x, y, and z? Variable or known? That's all the points in the plane, right? That's every single point. So when we write the equation, we leave it as x, y, and z. X naught, y naught, z naught. Known, it's a particular point. Any point, but a particular point in the plane. So we evaluate the dot product. We get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So here's form number 1, equation of the plane. Notice vectors are gone now. It's just an equation of x, y, and z. That's different than a line, right? In the equation of a line, it's a vector equation, right? It's a vector equation. This is just, vectors are gone. This is just a vector equation. Or, sorry, just a standard equation of x, y, and z. Okay, this will be for if you're asked to write the equation of a plane, right? So you're asked to write the equation of a plane. You have to come up with two things. You have to come up with a vector that's normal to the plane and any point in the plane. And then you've got the equation of the plane by using this. But when they give you planes, they'll often give you planes in a different form. So we can do the math here. So we do ax plus by plus cz. I'm doing 2 steps at once. Is that okay? Equals ax naught plus by naught plus cz naught. Is it okay? I distributed and I moved all these over to the side. Is it okay? Now what is that over here on the right? Ax naught plus by naught plus cz naught. That's a constant, right? So we'll just call it d. So it's just a number. All those are known values. So we get ax plus by plus cz equals d. Often when you're given planes, you'll be given them in this form. So what do you know right off? So you're given this plane, you're given a plane. What do you know right off the bat about the plane? Just by looking at the equation like that.
It's normal to the vector created by A, B, C.
Yeah, so your coefficients of x, y, and z will be your normal vector for that plane. Right? So you just pick off the coefficients of x, y, and z, and you got the normal vector. Okay. Now, what about generating points? How can we generate points on this plane? So ABC is normal. So I want to get some points on this plane. What would I do? What would I do to get a point? So for instance, I've got negative 2x plus y plus 5z equals 1. And I want to generate some points from this plane. What can I do? Yeah.
You can just assume x and y are 0 and then solve for z.
Okay, so let x and y be 0. So then we'd have the point 0, 0. What would it be? 1/5. Right, so all points on the plane are points that make that equation true. If you've got an ordered triple that does not make that equation true, then what can you say about that ordered triple? Doesn't lie in the plane, right? So all ordered triples that lie in the plane will make that statement true. Otherwise, they don't lie in the plane. How can I generate another point? Okay, so I'll make y and z 0. Then x is maybe 1/2. Okay, so how about one without zeros? How can I get one without zeros? Yeah, so you just pick any two numbers for two of the variables that you want, and then the third is defined, right? Can we do that in our head? So what's the point? 1, what's 10 on this plane? Mental math. $51? 1 minus 50 plus 2. Is that right? Okay. There's another point. 1, negative 4. So I just picked 1 and 10 for x and z, and then figured out what y was to make the equation true. If the ordered triple makes the equation true, it's a point on the plane. So that's your mindset when you're generating points. Okay, so if you're trying to write the equation of plane, exhibit A, right? If you're given the equation of plane, it could be either, but it's often exhibit B. And then you know right away what the normal vector is just by looking at the coefficients, and then you can generate points.
That can be and then one on your right, the future
Is that a stretch or a question?
No, it's not.
You're given these two, you have to Isn't the cross product how orthogonals are? Does the cross product give the next one orthogonal? Oh wait. Well, so if we show these two lines in parallel, they're in the same plane. No, not necessarily, because it could be like, oh yeah, because it could be like that. Like, yeah, but like, if they get
Okay, if you want to check 1, 2, and 3, I did 1, 2, and 3 on the board. Check your answers. Okay, so that was 0, 1, and 2, not 1, 2, and 3. There we go. Not A. Need to either do 3 or 4? Are we good? Which one? 3 or 4? 3? So, we're writing an equation of a plane. We need two things. What do we need? We need a point, any point on the plane, and normal vector. Anything we have right off the bat, just from the given information? Do we have a point, or do we have the normal vector right off the bat? Yeah, pick either point on the line. We have a given points on the line, and those are all going to be points on the plane. So take your pick. 1, 3, 4. Look, we're half done. Okay, so now I've got these lines, and these lines form a plane, right? How am I going to get the normal vector to this plane? I'm going to get the normal vector to this plane that contains those two lines. Okay, so what is 4, negative 2, 5? What is that? Isn't that the parallel vector to the first line? Are we good? And then what's negative 1, negative 3, 2? That's the parallel vector of the other, right? It's the direction vector of the other line. Negative 1, negative 3, and 2. So if it's the direction vector of the line and that line's in the plane, then how does that vector relate to the plane? How does this red vector that's the direction vector of this line relate to that plane? Is it orthogonal to the plane?
No, parallel.
Parallel, right? Or we could put it in the plane, right? We could set it right in the plane, or it's parallel to the plane. It'd be up here, but it's going to be parallel. And then same with negative 1, negative 3, 2. And what are we after? What are we after? Well, yeah, we need a vector that's orthogonal to the plane. And I've got two vectors parallel to the plane. How can I get a vector that's normal to the plane? You'll be the cross product of those two, right? See that? That's exactly what cross product does. It gives you a vector that's orthogonal to your original vectors, and therefore orthogonal to the plane of the original vectors. Hear that? Plane. That's what we need. We need a vector orthogonal to the plane. Right? That's what we need. So we can get that by. So we got our algorithm, right? IJK. Doesn't matter if it points up or down, whatever. This is the one that will point up. If I go 4, negative 2, 5, cross -1, -3, 2. And we're going to do the determinant to get the normal vector. Okay, so my I components down and to the right and add, right? So -4i, but then plus 15i. So my I component going this way. So it's going to be -4 plus 15. So what is that? 11. And then j. Down to the right is -5. Down to the left is -8. I see -13. Okay, down to the right is -4. Down to the left is -6. So, -12 and -2. So -14. That's the cross product of my red and my green vector. And therefore it's normal to the plane. So now we're home free. And then if you want to get it in the other form, it's a piece of cake, right? Just do the algebra. Remember the cross product, what it does for you. Given two vectors, those vectors create a plane. Your cross product will be a vector orthogonal to that plane because it's orthogonal to the original two vectors. Got to remember that. So 4 is similar. Instead of giving two lines, now you have a line and a point. So it's going to be a similar thing. Your point is, you're done, you got it? So given a line and a point, how can you come up with a normal vector to the plane that has a line and a point? Almost the same as this. You just have to, kind of create the situation again. And then you're doing the same thing.